This conference will now be recorded.
Right. So before that, if you before.
This conference will now be recorded.
Fine. So let's quickly have a look into the topics that we had discussed yesterday, and mostly what we were talking about in yesterday's discussion was the non the concept of stationarity. So we saw that let's say when we are doing CCAR, or let's say when we are doing the IFRS 9 models, so whatever, so macroeconomic variables play a very critical role, and in CCAR our objective is to see how is it that you know so how is it that these macroeconomic variables are responding to the balance sheet component and the P&L statement component. So how do they look when the series is stressed, right? So that is one of the important topics that we had been. So that is what we were talking about in yesterday's class, and we saw that when we are trying to incorporate the macroeconomic variables, right? So my objective is, let's say there is the interest income. I want to know how is it that this interest income is related to the macroeconomic variable. So over there, I would be applying the linear regression. But because it is a macroeconomic variables, before developing the regression, we need to work on some other things. We need to ensure that the data that we are inputting, like the macroeconomic variable data that we are putting in, is a proper data set. I mean, those variables are actually proper, right? And given that, right, so given that, what we can also then what we can do is we can try to, even that we ensure that the data is correct, then from there we can kind of develop these concepts of so then we can develop the linear regression model, validate that, and so on. But when we try to do that, what is the thing that we need to ensure? That the macroeconomic variables that we are developing are properly treated, and to treat them we saw that we need a few important things to look into. So what are those? First of them is stationarity. We need to ensure that the variable values which are going in are the fundamental values. So they are the long run average values. Now, when they move from this long run average value to to reach to this long run average value, and to ensure that their fundamental behavior is only captured, or the long run average behavior is captured, what we need to do over here is we need to look into the only the permanent component of their long run permanent behavior. We would not ideally be looking into their so we would not be ideally looking into their uh, so what should I say, into their so we would not be looking into their temporary behavior, and that is where the role of stationarity comes in. The stationarity checks helps us ensure that all the temporary movements in the data is taken care of, they are extracted away, they are removed, and what we are left with is this particular data set. So is the long run average behavior or the permanent behavior, right? So that is what we had seen in the discussion yesterday, right? Also we talked about concepts like so basically how is it that we can test for stationarity. To test for stationarity, we would need to have a look into the ACF and the PACF graphs. We also saw that when is it that the ACF and the ACF graphs would kind of decay. So we saw that the ACF would exponentially decay on the lag when it is stationary in nature, right? So ACF does not decay over, if the ACF is not decaying over extensive lags, we know that there is an element of non-stationarity. So that the data is non-stationarity. There are certain temporary characteristics which is impacting the data, right? So that is something that we have seen in the discussion yesterday. So from there, the next question that comes out to us is the following: then how do we test for ACF, and how do we, given a data set, how do we do that, right? So over here, we have this data set called the time series data. So it's an airlines data. The objective of choosing an airlines data is that all these uh, abnormalities that we are generally talking about is something which will be there in airlines data. Why would it be there? It would be there because of the reason that there is a cyclicality or there is a seasonality involved in airline bookings, right? This is a festive season. So now you will see that the air prices are, airline prices, ticket prices are relatively higher than they remain normally throughout. So this is where this thing needs to be taken care of. This is where we need to look into it. So over here, so that is the reason why we are using the airlines data. So when we use the macroeconomic variables, so I'll also use the macroeconomic variable data to show you that how those tests are to be done. So let's first of all try to understand how to read those reports in SAS. So first of all, if I have a look in here, it says so what I'm trying to do is, I'm just trying to create out the month, year and quarter. So these are three basic date variables I'll be creating, and I'll create a backup data set called airline data. So so I'm not kind of, yeah, so I'm not kind of like what tampering with this master data file time series airlines. I'm just trying to create an alternate data and would be doing my treatments on that. So let's run the record. So let's run the result, the data set over here. Right. So over here you would see that it is 144 observations and 5 variables. So let's have a look into the data file over here. So the data set is here. This is your airline data, right? So if you look into this date, right? So it says that it is Jan 1949, Feb, March, and so on. So and the number of passengers are over here, and the months are over here, and so on. The year is over here, and the quarters are over here. Now let's say I want to summarize the result at a quarterly level, I can do that. If I want to do it at an annual level, I can do that. If I'm doing it at a monthly level, I can also do that jolly well. Or if I want to do it per month, I can do it as well. So I have created these three characteristics so that they would help me categorize the time series data or report the movement in the time series data, right? So this data varies, starts from 1949, Jan 1949, and it goes on till December 1960. So and the records are, so this is 12 years of data. So 12 into 12, that's 144 months of data, right? Now this time series process or looking into stationarity as assessment of this entire time series models, so they are dependent on the assumption that the number of observation must be more than 50. Okay, so now over here, so the first thing that we need to do is we need to have a main idea about the main descriptive stats of this time series, right? And the next thing that I need to address over here is that whether this is actually a time series or not, right? Now, what do I mean by the point that whether it is a time series or not? Because if this data is not a time series data, then there is no point in doing the other tests, right? Now, to assess whether this time data is a time series data, what we need to check is that whether the lags, right, are, or the autocorrelation across within the lags are white noises or not. Now, what do I mean by this? Let's say that this is a time series, right? Now, if it is a time series model that I'm developing or I'm testing, right, then the basic assumption of the time series model is that y in the TN period would be a function of, or would be explained by y in the t minus 1th period. Y would be explained by t minus 2th period. Like this, y in the t minus kth period. So obviously, one thing is very important, one thing that remains important is that there must be an element of correlation between these lags, right? So the autocorrelation between one or more lag must be statistically significant. Now, if all the lags are not correlated amongst each other, right, it means that this entire process is a white noise process, right? So over here, so the first step, what I'm trying to do is I'm trying to do two things: get an overview of the data, or that is the number of passengers, the average number of passengers, the standard deviation. And what I'm trying to also do is I'm trying to understand that whether the autocorrelation is, so what is the autocorrelation and so on. And the second test that I'm trying to do over here is I'm trying to look into the significance of the lags. So whether the correlation across the lags are statistically significant or not. So correlation across lags are statistically significant or not. Across lags are statistically significant or not. Are statistically significant or not, right? Or as we call it, the whiteness of the error term. Okay, of the autocorrelation coefficient. So let's run. Now, before running this, let me introduce you to the component of this code. So the ARIMA procedure is the procedure in SAS to execute the time series model, the auto-regressive integrated moving average set of time series models, right? The next part is identify. This identify statement helps us identify the basic descriptive statistics of the time series model. Now, what is that variable for which we are going to do this, right? So what is that y variable that we have over here? It is passengers. So passengers means the number of passengers, and I try to predict the number of passengers that will be there in the next 12 months and so on. And it says in lag equals to 90. Now, what is the number of lags up to which I want to understand the correlation of the borrower? So up to which I want to understand the correlation between the error between the lag components. So that in lag, number of lag is equal to 8, right? So over here, if I run this code, let's run this code. Yeah. So this is what the outcome looks like, right? So over here, it reports the mean of the working series, and it reports the standard deviation of the series, right? So the mean number of passengers onboarding is 280 with an average of plus minus 119. So over here, this is your ACF function, or the autocorrelation between the lags. Now, this is the inverse of partial autocorrelation. We will not look into that. What we will look into here is this result, the autocorrelation check for white noise. Now, these are the respective autocorrelation for the first six lags, right? So over here you can see that these are the ones between the first six lags. So these are partial autocorrelations. Yeah, these are the autocorrelation for the first six lags, right? Now the question is that
In the
are
6
these
lakhs
lags?
or 8, we are checking this one, the last tab, up to like 6. It's showing up to like 6. we gave
Yeah, so by
8.
default it goes up to 6 lakhs.
Oh,
So basically, if I see that, so the so if you have a look into this 1, 2, 3, 4, 5, 6, right? Now, basically but if you look into this correlation table, right, you'll see it reports up to 8 lakhs. But when we are just summarizing, we just looking into the last 6 lakhs is enough. Now, over here, if you think about it, you will see that. So what does this particular report tell me? Now, this report tells me that I have an autocorrelation of 0.94 for the first lag between Y0 and the first lag. This is between the Y0 and the second lag, Y0 third lag, Y0 fourth lag, fifth and the sixth lags. Now, are these autocorrelations that I am seeing in the last 6 lags, are they statistically significant? Right? Now, when you do this, when you are reporting this, so now I need to do a testing exercise, right? So what is the test hypothesis over here? The null hypothesis is that the autocorrelation coefficients are white noise. That is, the autocorrelation coefficient that I see between the lags are not statistically significant, right? And the second over here is the autocorrelation coefficients are not white noise. So the alternate hypothesis says that no, the autocorrelation that I get to see is statistically significant. So there exists a significant correlation, autocorrelation between the lags. Now, if that exists, if that a significant autocorrelation exists, then what we can clearly say is that yes, the time series model can be, so this can be developed as a time series model, right? So over here, since I can see that the so over here, if you so basically, how do we reach to our decision of statistical significance? So what you can see over here is that P is less than 0.05, then 80 is rejected at 5% level of significance. So over here, if you have a look into the result, you will see that the p-value over here is actually very small. So if I consider these autocorrelation to be statistically significant, my chances of committing a type 1 error is actually very small, and hence the lag up. So the lag we consider over here is considered to be a significant lag, right? Sorry, the autocorrelation between the lags is considered to be statistically significant. Now, given this, what I can say is that there exists significant autocorrelation between the lags, and hence this model or hence this variable is a proper time series variable. So this first check, even before you do a stationarity check, the first check that you are trying to do over here is you are trying to understand whether a time series model can be applied on the data. Now what we'll do is we now next move out to the decomposition of the components of the airline time series. Now over here, what we want to understand is that what do we think of how the series is actually behaving, right? So is it this time series a stationary time series or not? Now, one very simple concept for stationary time series is that we know by definition that a time series is a stationary time series if its mean and standard deviation remains constant across the data, right? So if there is, so if what we want to understand over here is that whether there is some kind of so whether there is some kind of what should I say? So whether there is some kind of uh, a situation where as I keep on taking subsets of the data, the mean keeps on varying. So whether there is a trend in the mean, cyclicality, seasonality in the mean behavior, average standard deviation behavior or not. So that is what we are trying to do over here. So what I'll do is I have the variable passengers, right? And I have the class year. So by year on year basis, I'm just trying to understand how the mean is varying. So I'm doing a simple proc means over here and trying to put that result out in airline mean summary. So I have the data run over here. Now, one thing that you would get over here is yeah. So to every mean, you will see that the average is actually varying, right? So if I take the first year, this was the mean. Next year, this was the mean. Third year, this was the mean. Then you have an increase. There is an increase, 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 and it keeps on going on, right? So, so this gives us an idea that the mean throughout has not been very consistent. So there can be element of cyclicality, there can be element of seasonality, and so on, right? So over here, if I look into the airline mean summary, I get an idea that there is, so the mean values have been changing and across the subsets. So across the subsets, if we look into them, we'll get to see that the mean is very different, right? Now, one thing that you can also do is, apart from using year as the class variable, you can also use quarters as the class variable as well. Anyways, so first let's have a look into the plot. So I have the average and the year, and what we are doing over here is a simple graphical plot. Okay. Now, if you have a look into this mean by no way looks a straight line, right? So, I mean, it's not a flat straight line. It's not a constant mean. The mean is changing at each point of time, and clearly there is a linear trend to this mean, right? So this mean is linear and positively slope, showing that there are certain trend elements involved in this mean. So, so one thing that we can clearly see over here is that there is a linear trend, right? Now, the question that comes out is this trend, right? So is this trend temporary or permanent? So over here, I have seen this trend and it has been increasing. So what we need to first of all do is we need to detrend the series. Also, another thing that we need to look into is whether there is a seasonal effect on the data, right? Now, if there is a seasonal effect, now the sales would tend to spike up in every quarter. And hence, what we have done is we created another data called the airline seasonal data from this raw data airlines data. And we created a quarter indicator, right? Where we concatenated the year, 0 and the quarter. So basically, if it's 1949 first quarter, it becomes 1949-01. If it is the second quarter for 1949, it becomes 1949-02, and so on. So if we observe, if we have a look into this airline seasonal data, so this is how the quarter-wise indicator looks like, right? Now what we'll do is we'll do a proc means. And when we do a proc means, we'll get an airline seasonal summary. So quarter-wise, what we get to see is we get to see that the sales are the number of passengers, the average number of passengers, and like quarter-wise, how is it that they are working. So 1949-01 will comprise of 3 months, Jan, Feb, March, then April, May, June, and like this. So over here you see that 1940, so this is 1901 first quarter, third quarter, fourth quarter it goes down, right? And again it spikes up in the first quarter, goes up in the second quarter, third quarter, and again in the fourth quarter it goes down, right? So number of passengers keep on always relatively falling, right, in the fourth quarter. So there is, I can, if I plot this, you'll see that after, at a regular interval of time, like relative to what the other periods are, the sale always drops in the fourth quarter, or the number of passengers always drop in the fourth quarter. So over here is 157, 171, 194. Again, it drops in 1904, right? So every time, so it may be that on the whole, because there is a linear chain, right? The lower values are going higher at every month. So if you look in 1949-04, it's 130 versus 1950-04 is 129. Then 1951-04 is 158. Then it's 185.867. So it is growing because the trend is positive, and there is a positive linear trend, and it's growing gradually. But every time the sales are dropping in the fourth quarter, right? So if I look into this data in this way, I can say that yes, there is an element of seasonality into the data. So what we do is we just run this code again now with the quarter indicator and the average. So every time you look into this, you'll see that it rises up like this, it goes down, again rises up, it goes down, rises up, goes down, rises up, goes down, and this plot comes out, right? Now, another way we can look into this plot is, I can do a very simple proc print and take it into an Excel and look into this. Time series results. Airlines data. Okay. So now if we just put in an insert over here, this is the average. Okay, so over here you have the years, and over here you have the graph, right? So one thing that you can clearly see is that if you put a fixed mean, right, a constant mean, then also the model, this is so this is not only that it's non-stationary in mean, it is also non-stationary in terms of variance, right? So the question, so basically let's say if I want to put up a trend line to this, now can I exponentiate, or can I kind of capture this by a linear line? If I look into the linear line, you will see that there is possibly a linear line, right? But the variances have changed. Or if I want to kind of predict it by a horizontal straight line, the variances are changing throughout. So it is, so given a variance, and if you try to map it into a linear line, right? So what is the fit which is coming in over here? So it's an 88.2% fit. So which shows that it is not really a very good fit over here, right? So because why is it not a very good fit? Because even though here the variances were less, if you look into this part, if you look into this part of the series, so if you have a look into this part of the circle, right, and if you have a look into this part, this part, so you will see that the variances have largely increased, right? So over here, the set of variance in this part of the subset of the data, and the variances in this part of the data, they are two very different set of variances, and hence what I can clearly show is that what we can clearly show from here is that this data is not only like non-stationary in terms of mean, but it is also non-stationary in terms of variances. And what we also get to see is that at a quarterly level, every quarter and every fourth quarter, the sales gradually go down. But given that there is a trend, this prediction remains. So the values keep on going higher, but it is always relatively low relative to the first three quarters. So over there, I can also say that the element of uh, seasonality exists in this particular data. So this data has both trend and seasonality involved into it, right? So any questions up to this part?
So Tanmay, so like this. So when we are doing a CCAR model, so the variables would be like the way we are plotting against passengers, it will be like GDP or unemployment, that variable.
Correct, correct, correct,
Okay.
correct. Okay, fair enough. Right? So now the next question that comes out is that how do we detrend the series? So over here, what I saw is that there is a linear trend. Right? So what I need to do is I need to develop. I need to first of all detrend the series then. So what I have done is I have this data, the airline trend. I have created this data airline trend, and over here I'm like keeping the first observation as the value and observation as the value, so that I'll be fetching out that one single observation from the data, and I will assign a new variable t with this particular value, with that particular value of that iteration. And like this, what we have is, so we have around 144. So basically, if you have a look, so in this airline trend data, what I am trying to do is, I had this data, right, 1 to 12, 1 to 12, like this. So I have created a new value where it is running from 1 right up to 144, right? Because there are 144 observations. So over here, one thing is very important. So why am I creating this t value? Now, first, what I want to know is that if it was only time which was predicting the, which would have predicted the future values, then what would be the predicted passenger values, right? So if I remove that value from this, if I remove that value from this data, right, then the remaining value that I have will be something which is the detrended series. So over here, now if you have a look, so what have I done over here? So I have taken 144 observations. So basically, if you have a linear trend and you want to descend the series. So now let me just talk something more about this stationary and non-stationary part. So we had been talking about the stationary non-stationary part, but what we have not talked about is the way of differentiating the series, right? So way of converting the non-stationary series to a stationary series. Now there are two parts to it. There are two ways. One is called a detrending. So basically, if you have a linear trend in your series or non-linear trend, so that trend is removed, and the other is differencing. So the error terms are differenced. Detrend and differenced. Now the next question that comes out over here is, so the next question that comes out over here is that how do I detrend a series? Now, the basic idea of trend is that the variable yt that you are seeing or that you are plotting is only driven by time. So if it was only driven by time, how would that, or what would that series look like? So that is what is the trend component. So a trend is very simply estimated like this: yt as a function of time. So it's a plus b dot t. So this coefficient of beta, now if this beta is statistically significant, right, then I say that yes, there is a trend component in the series that you are trying to plot, right? So over here, that is what we are doing. So I created this t variable over here, right? So the first observation takes the value 1, second observation takes the value 2, the third observation takes the value 3, fourth observation takes the value 4, and so on.
So means we are giving the coefficients value, right?
Not the coefficient values. I am just trying to create the t variable. So over here I have passenger. So passenger is my y, right? And t is my independent variable over here, my time. So if there is a trend in a variable, so as the time changes, the passengers will change, right? So even if everything else remains unchanged, just due to the change of time, the passengers will change due to a change of trend. Let's say it is very trendy to fly in an aircraft or take a flight. In 1949, it was really very trendy. So it may appear as a short-run trend, right? And people may feel better off or may seem as it has to be a status symbol that they take a flight and that they travel. So with time, if your passengers or if your estimates change, then that is called the uh, so that is called the movement due to trend. Now, when I talk about trend, so what we are trying to understand is this: does time have a significant role to play in impacting the number of passengers? So is it that as time is changing, the passengers are also changing? Because what we got to see was a strong linear trend in there. So over here, the next objective is that I will regress. I'll do a linear regression of the passengers on time, right? And what we try to understand is that does time explain a significant variation in the passengers, number of passengers booked over the quarters. Number two is we try to understand that is there a significant causality between time and passengers. So is it that time is an important variable in explaining variations in the number of passengers? So over here, what they do is the following. So what I do
Then
is
by
I just, yeah.
we are doing this regression because from the graphical representation we saw there's a trend. If had it not been there, so we wouldn't have done this, right?
No, even if we see that graphically there is a trend, we need to estimate or we need to check whether that is a statistically significant trend or not. So I may have a trend, but if it's not statistically significant, I'll just ignore that. But over
And,
here, the trend was a very strong linear trend, and I believe we will get a statistically significant coefficient between y and t.
and if we see no trend, then we don't at all get into
Then,
this
then we don't
regression.
do anything. Correct, correct, correct. So let's have a look into the results. So we start with the first table. So this is your analysis of variance table, and it comprises of model sums, model squares, errors, model sum of squares, error sum of squares, and finally what you have is the mean sum of squares. Right now, the mean sum of squares is the sum of squares divided by the degree of freedom. The error sum of squares is divided by the mean sum of squares is the error sum of square divided by its respective degree of freedom. And what you have is the mean square. Now the f value is, as we had talked about, gives us an idea about the variation, the explained variation that I have relative to the unexplained variation, right? So I say that so my ESS by RSS is equal to 828. It means my explained sum of squares is 828.2 times my unexplained variation. Now, what is the probability I would commit a type 1 error if I consider this as a significant multiple? My probability of committing a type 1 error is less than 0.0001. Hence, I can say that the overall variation explained is very significant relative to what is not explained. Hence, the overall fit of the model is considered to be very good. Similarly, if I look into the adjusted into the R square and the adjusted R square, both are above 85%. So I can say that time alone explains 85% of the variation in the dependent variable, that is the number of passengers. So it tells me that yes, time is a very strong explanatory variable in the trend. So the trend component is actually very high. So over here, when I come, I see t and the parameter estimate 2.65718, and the p-value is less than 0.0001. So it says that yes, the causality between time and the number of passengers is actually very significant. So what are the predicted values? So if I have this trend, so then what are the, so how much of that value is due to trend? So over here, what I do is I create a new variable called passengers predicted, right? So, so if you look into this airline trend value, you will see that. So airline trend. So over here you have the passengers predicted, right? So 112 passengers, out of which like 90 is because out of this value you can say that 90. If time was to predict the values, it would be 90. So the difference is the detrended value, right? So how do we reach to the detrended value over here? What we do is a very simple exercise. We say that the passengers detrend is nothing but the total number of passengers divided by the passengers predicted, right? And what we are trying to do over here is we are trying to multiplicatively adjust the trend. So over here, when I detrend the value, so the detrended multiple is 1.24, 1.40, or something like this, right? Now, also another thing that you could have done over here is you could have subtracted them, right? So you could have subtracted the passengers, and from there you would have obtained this. But the point is, there can be some values which may go negative. Let's say, for example, over here, the actual number of passengers is 118, but the predicted value is 119, right? It is 104, but it is 116. So there it becomes a bit of a challenge predicting negative values. Because of this fact, right, what we have done is we have trended the value. So whenever the trend is not very strong there, so the trend is going to hugely over predict those actual values. So in such a case, the fractions become very helpful in helping you explain the overall behavior. So that is why we had done this division over here, right? The next thing that comes out over here is, now once I have done this, I need to know, I need to ensure that that the trend impact is no more there. So now if I, on this detrended series, if I run a regression with time, the regression coefficients will be insignificant, right? So there was a positive trend, it should be greater than 0 but insignificant. So what we do is we run this, we just run this code. So this is just a cross check to see that the detrending has been done correctly.
You are doing some kind of this calibration fix.
Yes, you can say kind of. So I would not use the term calibration over here. I would say the term adjustment. So I'm adjusting it to the trend. Now, given that some trend values, some predicted trend values had been over predicted, right? The actual value was 104, but the predicted value was 116. So if I had done this actual minus predicted, I would have got a negative value. So in order to prevent that, what we do is we divided the predicted value. This to get the ratio, the multiples, right? So then later, once we have predicted it, we can always go back to that equation and we can uh, reach back to the, so we can add back the trend values and we can see wherever it was required. Wherever required, we can add those trend values back and we can see how much the figure was. But the initial prediction that we are making is in terms of the detrended series. Now over here, one thing that you see is, first the p value is high over here. The f value has gone down. the R square is 2%, and the sign is spurious over here. It was a positive trend, it shows negative, and the p-value is also very high over here. Hence, I say that on this detrended series now, time is not an important explanatory variable. So the series has been appropriately detrended. So the first objective that we had over here was to check that how is it that, so the first objective that we had was to assess that whether the time was playing a critical role. Once we see yes, it was playing a critical role, what we did was we had removed the data. So we removed the uh, so we remove the the trend component from there. The detrended series, we did a regression on time. We see that now we see the time has become statistically insignificant. Now it has become statistically insignificant because of the fact that the trend component has been removed, and hence the T is statistically significant. But not only that, but it also now has a spurious sign. Right? So the first problem of detrending the series is sorted. So now one thing that we want to know is that how would the detrended series look like? So one thing that you can now see over here is that this series that we have over here, right, does not have that kind of a mean which it was showing previously, right? Now the series has kind of stabilized. So that trend component has been removed from the series. Now, how did you remove that trend component from there? What you did was you had kind of done the prediction, right? So what you did was you had the predicted values, you had the actual values, and you had done a ratio. So anyways, anytime using that formula, you can go back using that. This is the ratio. You can always go back to the actual number of unpredicted values, right? And from there you can find out, okay, what was the actual number of the borrowers which was there, and that will give you your detrended series. Right. Now, however, so over here, now the next question that I need to study is that is this series now stationary in nature, right? And to do this, there are two things that we will talk about. First, we'll talk about, so there are two things we need to incorporate. One is the MINIC criteria. MINIC is minimum information criteria. So to what correspond to which lags is the Akai information criteria, and the Schwartz-Bayesian criteria is the minimum, right? So we need to look into that, and over here we need to therefore talk about the information criteria as well. Now I need to do a stationarity check, and to do the stationarity check, I use the ADF test, right? So ADF test is the so this is augmented Dickey-Fuller test. So what you specify is the first to the 13th lag. So those are the last 12 lags that you want to always take up. You want to start from the first lag and go up to the 13th lag. So those are the two things which are specified over here. Now when I run this code, what we'll get to see is we'll see that the ACF plots and the PACF plots are generated. The minimum information criteria is generated, and from here we can optimize, or we can try to find out the optimum lags that we would be using in our model. I mean, the optimal lag as in so whether, first of all, we try to answer whether it is stationary or not, and then we try to find out which is the lag of the series that we are going to use. So let's run this part.
No, I got little confused. This lags the quarter, huh? No,
Sorry.
I got little confused. Lags meaning like first quarter, second quarter.
So it can be your first quarter, let's say output, this GDP this quarter is explained by the GDP last quarter, last quarter, last to last quarter, or it could be month, it could be years, so whatever it is. But over here, because the data is in a monthly basis, the lag is a monthly lag, right? So if you look into the raw data, right, the detrended, if you look at the detrended data, have a look into the detrended data. So originally your date variables are what? Is month, right? I created them for summarization purposes, but originally my this thing is uh, Jan 29, Feb 29, March 29. So the lag is, so basically if I go back 1 year, so it is 12 lags. So I start from the first and I'll go to the 13th lag. So I'll take up a list of 12 lags. Now, if you have a look into the formula for the mathematical formulae for the ADF test, you'll get an idea about what this 1 and 30. But let's not worry about it at this stage. So basically what I've done is I've put in 12 lags at a go. Now I'll run this code. Right. Okay. So now what you will see is you will have autocorrelations over here. And we'll try to see whether how the partial autocorrelations look like and what is the statistical significance of the lags, what is the minimum lag that we have over here, and so on. So we will be looking into them, right? And we try to assess that after detrending, has the series become stationary or not, what else can be done, and how do we go ahead with it, right? So that is the next part that we'll start talking about, and that is what this result talks about over here. Now, one thing that we have clearly seen is one thing that we have clearly kind of seen is that if it's a statistically, so if it's a stationary series, the exponential lag, so those lags would kind of decay exponentially, right? So it will start going down gradually one after the other. And if at any point of time there is a reversal in the autocorrelation and suddenly it spikes up in between and then again goes down, again spikes up in between and then again goes down, then you know that there is an element of seasonality. So we need to check all our graphs for these things, right? So over here, it starts off with, because it has the identify statement, it starts off with the periods of differencing that are going to be used. So there are 12 periods of one. It starts from the first period of differencing, and it would go up to 12 periods. Now over here, let me just try to walk you through this concept of differencing. I'll come to this concept, but let's first try to understand the part that we were trying to look into. That is this time series a stationary time series? How do I interpret the autocorrelation functions then? Right? Okay, guys, just give me a minute's time. I'll just be back and we'll get started. Okay, so let's start having a look into the correlation functions, the way the autocorrelation functions are done. Now over here, it is not always necessary that the autocorrelation function should only be on one side, right? So it would be so it would be such that it could be positive as well as it could be negative and so on, right? So one thing that you get to generally see over here is that the correlation coefficient can lie on both sides. So if it is on this side, it means that between yt minus 1 there is a negative lag. This means there is a positive lag. And ideally what we should expect over here is that the lags should keep on kind of decreasing, right? It should kind of keep on decreasing exponentially. But if you have a look over here, you will see that 0.35, 0.15, 0.20. So after the first two lag, the third lag suddenly shows a spike up, right? So this is the 0th lag, and this gives the correlation between 0 and the first lag. This gives the correlation between 0 and the second lag. This is between the 0 and the third lag, between 0 and the fourth lag, right? So basically, if it is, if yt is y1, then this is the one between 1 and 2, 2 and 3, 3 and 4. So again, what you see is suddenly that the correlation rises. So after that, the fifth, sixth, seventh, eighth, it goes down, but in the ninth, again it rises, right? So this decreasing order of the correlations is not really very, uh, so what I would say, it's not really very consistent, right? Hence, what we can actually say is that yes, there still exists some element of there still exists some element of non-stationarity over here, because there was a cyclical movement, there was a seasonal movement, right? So which you can see, right, when this spike happens at a very regular interval. So you can clearly see that yes, there is a certain spike which is happening at certain points of time, right? So which should not ideally be happening. So therefore, one thing that we are saying, one thing that I am saying is that yes, this part or this series is still a non-stationary series. Now, one thing can also be the fact that you may have some significant autocorrelation or something, but after a certain lag, if this goes down, let's say up to the sixth lag, you see that the autocorrelation is significant, but after that it becomes statistically insignificant, then you need not bother about those, right? But if you have a look over here, from the first six lags, the autocorrelation remains statistically significant. 12 lags, 18 lags, 24 lags. So the first 24 lags, it remains statistically significant, right? So one thing that we can say is that whatever the autocorrelations that we are observing for the sixth, so from the 12 first to the sixth lag, sixth to 12th lag, whatever. So each of these are statistically significant in nature, right? So therefore, I can say that this series that I have, this series, this detrended series that I have, is still, uh, so this series that I have over here is still a non-stationary series, right? Now, onto this model, I cannot use much of exercise, any modeling exercise. So one thing that I can say is that if you try to develop this model, right, so up to a certain lag, so what out of all these lags that I have between AR and MA, it says that an AR of model 3, an AR model of order 3, that is 3 lags, will give me or has the minimum value. Now, what is this value? What is this minimum information criteria? Now, the minimum information criteria is a criteria which helps us assess whether a time series is, so which is that most informative model. So if I build up model with multiple lags, with permutations and combinations of multiple lags, what becomes important over here for me to understand is that which is that lag which is the most significant, which gives me the most significant or the best results, right? So to capture that, what we have is the information criteria, the minimum information criteria. So what is the minimum information criteria? The minimum information criteria is like the minimum information criteria is uh, like so the minimum information criteria is like it's that criteria, which will help you understand that the minimum so it will kind of help you understand this thing. Hold on, just let me rephrase this. So the minimum information criteria will actually help you understand that which is that model which is giving you the best information. So the mod which is that model which has the minimum residuals, right? Which has the least residuals. So the information criteria, so there are two measures. One is the Akaike information criteria, the other is the Schwartz Bayesian criteria. And both of them are functions of your so both of them are kind of functions of your this thing. So they are functions of the residuals, right? So what we'll try to do over here is just let me write the formulae for both of them. So you will be so you will kind of get an idea about what these two measures are like. So first talking about the Akaike information criteria. The Akaike information criteria. If I talk about the Akaike information criteria, it is represented as AIC equals to T into the natural log sum of squared residuals. The sum of squared residuals, or as we call it, the RSS, plus in natural log So basically, one thing that you can see, so what is this T over here? T is the number of usable observations, right? So over here, no, sorry. Sorry, this is not the AIC. This is the Schwartz spatial criteria. So this is a Schwartz Bayesian criteria, right? So one thing that you can clearly see over here is that it is a direct function of the residual sum of squares. So lower the residual sum of squares will be, lower will be the Schwartz Bayesian criteria. So similarly, AIC also has a similar formation, right? So if I write AIC, it is T natural log RSS, or the residual sum of squares plus 2n. So over here, if you have a look into this 2n, what is this 2n? N is the number of parameters which is estimated, right? So number of lag which are there. So each lag comes with a parameter estimate, right? So this is where this T log RSS, n is the number of estimated parameters and T is the number of usable observations. So n, if I ask, it is the number of estimated parameters, the number of estimated parameters, and T is the number of observations. The number of observations. So these are some of the important variables. So these are some of the important informations that we have. Right? So lower, so how do we use this? So, so how do you interpret that table? It says that let's say I develop a model with AR0, so AR1 and MA0. So if I develop an AR1 model, so then the archive information criteria will give me the figure 6.37, right? Now, what I want to know is I want to have this value as low as possible. Now, similarly, if I develop a model with AR1 and then if I keep on incorporating the impact of the random shocks and I start developing an MA model, the moving average models. So over there I see that the values keep on increasing generally, right? So it is always best for me to develop a AR1 model if at all I need to develop. So from here now what I'll do is I'll start rolling down along this way. So one thing that you see is that if I instead of developing an AR1 model, if I develop a AR2 model, the thing becomes at minus 6.35. Now, when I say it comes at minus 6.35, what it essentially means is that this is a higher residual. So this model AR2 will give you a higher residual than AR1 model. So between AR1 and AR2, it is always better for me to develop an AR1 model. Now when I move to AR3, I see that the information criteria becomes the minimum. It becomes minus 6.38. So when this comes in, so what you see is that this is something like, So it keeps on going down, and at AR3 this value is the minimum. Now this, according to the information criteria, then what it implies is that the residuals of this model, right, the sum squares of residual of this model is the minimum. Hence this model, if developed, will have the highest explanatory capacity. So looking into these values, what I would try to do is, by looking into this Bayesian information criteria, Schwartz Bayesian criteria, what I would try to do is I would look forward to develop an AR3 model. But again, this AR3 model, or this option of choosing the AR3 model, is dependent on the fact that this series that we have, or is dependent on the autocorrelation function of this series. But this series is not stationary at all, right? So this series needs to be stationarized. So by looking into the ACF plots, we can clearly see that this series is not really a stationary series, and this AIC, I mean the AR3, is not therefore a feasible option for us to develop, right? So
So you said that AIC should be minimum, right? So AR1
right,
has the minimum value, so we can go for AR1, right?
no, AR1 doesn't have the minimum value, right?
So it goes to
So
minus
AR1
6.25.
is minus 6.37, right? So
No, no,
minus
AR. Oh, yes, yes,
6.389
understood.
is a lower value than AR1.
Yes.
So I'll not go into the development part right now. So this is the way, we interpret the results to see whether the time series, whether a given time series is stationary or not, right? Now the next question that comes out is that, okay, fine, I see that the time series is not stationary over here because there is an element of seasonality involved in here. So then, what are the ways through which a time series can be converted into a stationary time series? Now, obviously, one thing that we saw was the trend stationary process. So by detrending, if you can actually convert a time series into a stationary process, then that becomes a trend stationary process. Now, what are the other ways of doing this? So how would you do that? Now the second approach that we have to convert a time series into a stationary process is the difference stationary process. So by differencing. Now the question is, what is this differencing and why is it that I say that a differencing can solve this problem? Now over here I have differentiated multiple times. I differentiated 1 to 13, and then I started developing the model, right? So okay, so just let me look into one more thing over here. We missed out on that. That is the partial autocorrelation function. Now over here, what you will see is that this is the partial autocorrelation function, right? 0.35. Now after this, you do not generally see very significant lags and everything, but there are certain correlation with the historical lags as well. Now, what does a partial autocorrelation function do? Now, a partial autocorrelation function has the following objective in mind. So, the autocorrelation, so when I talk about the ACF function, so what happens? In an ACF function, trying to assess the correlation between two lags. Now, when you are trying to assess the correlation between YT and YT minus 1, now YT minus 1 is also impacted by YT minus 2, and YT minus 2 is also impacted by YT minus 3, and YT minus 3 is also impacted by YT minus 4. So each of these lags are associated with one another. So the question that comes out over here is that how do I take care of that? So that is taken care of by the partial autocorrelation function. So what does the partial autocorrelation function do? The partial autocorrelation function reports two lags, the correlation between two lags after adjusting for the autocorrelation between them, after adjusting for the impact of all the other lags. So basically, let's say if it's a AR1 process, then what do we actually expect? That the the correlation between the lags of these two should be uh, okay. So basically, if it's an AR1 process, it means that the autocorrelation, the partial autocorrelation between lag 1 and lag 0 should be the highest and most significant, and after that immediately it should fall down, right? So it should go down to 0. Now if it's AR2, then the first two lags must be statistically significant, the partial autocorrelation, and then it must go down to 0. But what we see over here is that this is not really the case, right? It is not really the case over here. So the partial autocorrelations are also statistically significant. Now the reason that happened, the reason why we have this over here is because you know, so the reason why we have it over here like this is that there is this element of seasonality which is there, right, which has not been taken care of. So by how much does that value, so on an average what that value is, and how much is that value, how much should be removed from that to make that value non-seasonal in nature. So that is something that we need to take care of. So I am not going into the questions of solving the problem of stationarity. We'll do it with respect to macroeconomic variables. So my objective over here was to help you understand what exactly is this concept of stationarity, right? So to understand stationarity, we need to understand the concept of, so first of all, how to test stationarity. Number two, concept of ADF. Number three, the concept of ACF, PACF, right? Test of whiteness of the autocorrelation. So the autocorrelation tests, and we should also understand the concepts of this autocorrelation for white noise and the minimum information criteria. So these are the few concepts required to understand the concept of stationarity. And when you try to apply linear regression, right? So before you try to apply linear regression on a macroeconomic model, the first check that you need to do ensure is that the time series is stationary, right? And then what you do is you start developing your regression models. So any questions up to this point?
Sir, I have one question.
Yeah.
For the maximum order of lag, how can we decide that at which order of lag will be optimum level of lag we can take into the model?
No, the optimal lag choice, I'll come to it later. So this is not the part where we are deciding on the optimal lags, right?
Sure.
So first what we are trying to assess is that which are these, so are these variables stationary? If not, then first I need to convert them into stationary variables. Now we'll check out of these variables. Now we'll check for the long run association between variables. Now the variables which will not have a long run association would be considered, and out of the variables which have long run association between them, we'll do a causality check between them and choose the variable X which is impacting Y and not the other way around. So those are the next two tests of co-integration and causality. Once you have zeroed down on the variable, then with those variables, you just do a correlation. So you just take, you know, the macro variable, the balance sheet variable that you have, right? Once you know the key variables, and then what you do is you start with a zero lag, you develop the model. You start with a one lag, you develop the model. Two lag, you develop the model, and or you do a correlation analysis of uh, the lags with that dependent variable, and you see which lag it has the highest correlation, and you choose that lag as the most significant lag. And once that is done, then you have your macroeconomic variables together. You do your your transformations on those variables, and then you have your final data ready on which you run your linear regression.
So, sir, non-stationarity in time series model could also be responsible to some variables.
Sorry, I just missed you. Okay.
So, the non-stationarity in time series models can also be responsible to drop down some of the variables.
Yes. So if
Okay.
your variable is absolutely non-stationary and you cannot do anything about it, right? So then you can, what you can do is you can try out doing a log transformation or an exponential transformation, try to see whether you can stationarize that. Now, if stationarity is not possible in any way or the other, then you have to drop the variables. You cannot actually go ahead with the non-stationary variable.
Hello.
Yeah, take.
I'm having some basic problem in understanding. As in, say like it's a CCAR model, so here we are trying to relate the default rates to the macro variables, right?
Not the
Uh,
default to the macro
no,
variable.
not today. Like not today's class. I'm saying. I'm just like
Uh-huh.
so.
No.
So like how?
No. Even if you are talking about CCAR on a general basis, so what we are
Mhm.
trying to do, we are trying to relate the P&L statement
Right,
and
right. How
the item
income
in the
is
P&L statement
impacted,
and balance sheet to the macroeconomic variables.
and how income is impacted
Correct.
with the variable. Okay, let's just say now I have this. Say this is a macroeconomic data set wherein like instead of this airlines, I have like GDP and other inflation rate variables, and I
Uh,
have done like all these treatments and everything, and then I came like only two variables I selected. Came
Correct.
to the conclusion. Okay, GDP and say whatever. Say only GDP like, and then
Correct.
this this data having this macroeconomic data having this GDP variable, I would be incorporating in that other data, right? I mean, the what I'm trying to say is, uh,
So basically, once you have zeroed
uh,
down on the macroeconomic variables,
hmm,
right? So
hmm,
you have say 10 macroeconomic variables, right,
hmm,
which has been stationarized, on which co-integration checks has been done, on which
hmm,
causality checks has been done, right?
hmm,
Now, what you do is you want to find out which are the optimal lags. You have found out the optimal lags.
hmm,
So now
hmm,
on the dependent variable, you have that P&L statement item and its values over time, and you
right.
have the macroeconomic variables on the right hand side as
So
independent
how am
variables.
I incorporating this in that other data set where I have the dependent variable? I mean, because these are summarized data. I mean to say, I won't be. I mean, how do I making the merging the two data sets? Maybe I'm not able to understand. As in this macro data set, how am I incorporating with that income data? Uh,
So
So, so
basically,
she is saying that the income data is consisting of account IDs, and this is the
right.
summarized data.
no,
No,
why will
no.
it consider account IDs? So at a P&L statement level, you have your income, you have your expenditure,
Mm,
right?
mm,
Now, these income and expenditure heads will be available to you over a period of time, right? So they are P&L statement items. They are not account level information. So income statement, let's say interest income. So this interest income will be available to you over a period of time, right? So in the year 2000, you have reported you reported your interest income. In 2001, you reported your interest income. In 2002, you reported your interest income. 2003, you reported your interest income. So interest income, non-interest income, trust fee, deposit fee, your let's say So interest from auto loans, interest rate from your interest income from credit cards, etc. So you have all these maintained over a period of time. So they are also time series variables, right? Why will they be account level information?
Sorry, हाँ एक just actually got
So
confused.
account level information, the part from where you are generating your interest income final figures. So once you obtain your interest income, so first, so if you think about it, how will the data exist in the banking system? Interest income is comprised of what? Retail interest income from interest on retail portfolio, commercial portfolio, right? Now in the retail portfolio, the interest income earned is earned from each account, right? So at the end of every year, you will add up all the interest income that you have earned from the retail portfolio from all the accounts. You will add up all the interest income that you have earned from the commercial portfolio from all the accounts, and you club it together and you will get the interest income for that year. Now that is maintained in your system in a separate file, right? Similarly, say in 1990, the interest income was the 1981, that was the 92, that was the 93, that was there. 4, 5, 6 like this. You have it for 1992, say to 29, you have 30 data point, 30, 40 data points on interest income. So similarly, 30, 40 years of GDP variable, GDP values, unemployment, inflation rates, all these values are available to you. So your dependent variable is the interest incomes, right? Your dependent variable is your interest incomes at each time point, and according to the same time points or to the lag, whatever you have. So you have your macroeconomic variables reported there. So this on the left hand side you have a time series data. On the right hand side you also have a time series data.
No, understood. Okay, thanks.
Right? So in CCAR, everything boils down to this. So whenever you are doing a stress testing analysis or anything of this sort, so over here it boils down to your time data at a time point. Only then will you be able to assess how this thing is. Right?
And so one more question I have that
Yeah.
whenever we are going with the time series data with the such as GDP or unemployment rate, similar thing that we will do that, for example, you have created a T variable and all those stuff. The steps will be the same, right?
Yeah, the steps will be the same. Or what you can do is, if you are using a GDP series, you can directly run an ADF and see whether it is stationary or not. So I did it over there in a more broken down manner so that you can understand like what is being done and why is it being done.
Sure, sir. Understood. Can you please share us the code for that so we can practice it?
I'll share the code right away. Just give me. I'll share the code and the data set.
Hello. Hello.
Hello? Yeah, tell me.
Uh, Sir, can you please put in CC someone from among us,
From our
because
batch. Hold on.
sometimes
I'll
we get the delay.
hold on.
Like
I'll put
Vasu, you
some.
can also send it to Vasu.
Wait. I think I have written Devosmita's email ID and forward. Just hold on a minute. Just
Yeah,
let
not
me
not for everyone
attach.
because later we can decide.
Yeah. So just I'll just put it out. I have Devoshmita, Deepak. Oh, I have your mail IDs. Oh, so then I am just kind of marking 2, 3 of you over here. Okay. So I'm just sending it to a few of you. Just share it amongst yourself. Vasu, Shubho, Manish, Ashwin, who is Shobhishta is there, Himanshu is there. Fine. So I'm just sending it to you all. Just distribute it amongst yourselves. Okay. Someone please take the responsibility. Okay. Have I missed out anyone who is in the session currently? I have Debashmita over here, Deepak, Richa, Shashank, Vasu.
Sushil.
Sushil, Sushil, Manish.
She.
SINGH. SINGH SUSHIL.
Hold on.
SINGH SUSHIL.
Sushil,
486. 486 at the rate gmail.com.
486 at gmail.com. Right? Okay. Anyone else? Who else is there?
Akhilesh is there, I think. Akhilesh and
Akhilesh.
Manish from our batch.
I don't have Akhilesh's ID. Can someone, tell me someone? Can you guys tell me his ID? You can just tell me Akhilesh's ID, anyone?
Akhilesh FRM at gmail.com.
Okay. Akhilesh
FRM.
at gmail.com. Akhilesh is given there. Devasmita is there. Deepak is there. Sushil is there. Vasu is there. Fine. I've done it. Perfect. Hold on. I attach the SAS codes. I'll attach the data. Right? Okay, fine. So let's take a pause here for the day. You guys can practice this. So next class we'll talk about co-integration and we'll talk about causality and optimal lags. and we'll complete the data preparation part over there, and from there we'll move on to the next part. Okay, so thank you guys. Have a great week ahead, and let's catch up next week. Bye bye.